Well, good afternoon, everybody. Thank you for joining us. My name is Tom Davies, and today we're going to talk about modeling diffraction effects in thread. So first, just a little bit before we get started, for those of us who don't know the company so well, I'd just like to introduce ourselves and Photon Engineering's Fred. So CBS Europe is the main distributor of Photon Engineering's Fred optical engineering software. We provide technical support and sales for base in most countries in Europe, excluding Benelux, Spain, and Portugal. And we have branch offices in UK, Canada, and Japan. My name is Tom Davies. I'm COO of CBS Europe, and I've been using Fred and working closely with Photon Engineering for 14 or 15 years now. So, and I teach some of the courses, and I provide technical support help and write some of the documentation. So, diffraction modeling and coherence and physical optics in general is something that I've done a lot of, and hopefully I can spend the next half an hour with you and just explain an overview of what Fred can do in diffraction in the time that we have. So really just an overview before we get started. For those of you who aren't already Fred users and are joining us today just to hear a little bit more about Fred because you're interested in physical optics, diffraction specifically, what is Fred? Fred is a comprehensive optomechanical systems design analysis tool. It has both sequential and non-sequential ray tracing and multivariable optimization, and also the higher end of Fred, called Fred MPC, has GPU ray tracing support for ultra high-speed calculations. It can be used for a wide variety of applications, and I've highlighted 6 key ones here. Coherent beam propagation, which is what we're talking about today. Also, stray light analysis, scattering and ghosting effects in imaging systems, for example, and illumination system design and analysis, and generally speaking, virtual prototyping. Fred is a software where both the optics and the mechanics can come together, and you can really do a virtual prototype, tolerance testing of your system before it goes into production. So just a very quick overview of how Fred models physical optics. And it does so using a technique that we call coherent ray tracing, or more specifically, Gaussian beam decomposition. So first, physical optics. What is physical optics? It's a branch of optics that deals with coherence, diffraction, interference, and polarization, and other similar phenomena for which the geometrical optics ray approximation of ray tracing is not valid. So it's kind of the middle ground between geometrical optics, which doesn't include any wave effects, and rigorous electromagnetic theory. It sits in the middle between those two. So I'm using just this one single slide to explain Gaussian beam decomposition. It is strictly just an overview. The mathematics are available in a couple of published papers, and also in more details in our 3-day physical optics course. But generally speaking, the Gaussian beam decomposition algorithm is split up into 3 steps. What happens in Fred is that you create a source that you want to propagate through the system, and internally, that is decomposed into a collection of overlapping small Gaussian beams. And that's what these red Gaussian beam shapes are meant to represent. Then those Gaussian beams are propagated through the optical system using Fred's ray tracing engine in a way that allows us to keep track of what a Gaussian beam is through a collection of rays. And they refract and reflect through the system and so forth. And then when they reach the area you need them to, such as the detector, the Gaussian beams are coherently summed back together, and you get the field that you're looking for, a radiance or complex field, etc. So that's essentially the technique in a nutshell. Obviously, there's a lot more mathematics and specifics, but that's generally speaking what is happening. It's leveraging the Fred's ray trace engine to propagate Gaussian beams through the system and sum them on the detector. It has some advantages. The main one is that it is intrinsically non-sequential. Every Gaussian beamlet that you see there, and I say the word beamlet because it's a small Gaussian beam, each beamlet is independent from each other and can propagate on its own. So if the path is split off or some of the beam is clipped by an aperture, for example, this is inherently handled in the algorithm. Other techniques require that the beam must stay all together, and it's essentially could be a sequential process. Another advantage is that any type of surface can be ray traced. The only limitation is if we get down to the wavelength scale structures such as a grating, which cannot be explicitly ray traced. But any type of surface such as A-spheres, etc., can be traced without trouble. And experience has shown that Gaussian beam decomposition is more tolerant of large amounts of aberration. Again, some other techniques, physical optics, might have some sort of limitation there. And then the disadvantages of Gaussian beam decomposition is it gets a little bit more troublesome if we have very small apertures and it's clipping the field, because sometimes that requires us to resynthesize or resample the beam into a new set of smaller Gaussian beams. And that will become clearer as we go through the slides today. And speaking honestly, it's a little bit slower than other techniques because we have to decompose the source into Gaussian beamlets and then at the end of the ray trace coherently sum them again to obtain the complex field. So those extra steps there do sometimes take a little bit of time, relatively speaking. Often calculation time is not an issue with the coherent algorithm, as we'll see in some of the examples, but certainly that is an extra calculation step that needs to be considered. Okay, so today we're talking about diffraction. So I want to start with one of the simplest examples I can think of, which is quite simply a lens here. And here I'm using Fred's perfect ideal lens. And we're focusing a coherent beam onto a detector. And the detector's at the focal length. So that's quite straightforward. And then all we're going to do to simulate diffraction is let's put an aperture in front of the lens. So we clip the beam into this triangle shape in this example. So what do we need to do to simulate diffraction in this case? The wonderful thing with Fred's algorithm is that you don't need to do anything significant. All you need to do is make sure that the number of beamlets that you use to sample the aperture is sufficient. So what we have here on the left to the right is essentially the number of beams we're using to sample the aperture. And these circles here represent the waist of the Gaussian beamlets. So here we have, around about 3 beamlets sampling the aperture. And you can see here that the far field diffraction pattern just really is not accurate. It's a little bit chaotic. As we decrease the size of the Gaussian beamlets and therefore the number of them across the aperture, we can see we start to converge upon the expected far field diffraction pattern. And you can see here at the end here, this is pretty as we expect here with the 6-fold symmetry. And we have possibly 15 to 20 samples across the aperture. And you can see here, we need to make sure we do that. And if we do that, then Fred automatically, due to the clipping of this aperture and the abrupt cutoff that this forces onto the remaining set of Gaussian beams, when they are coherently summed, the diffraction is inherently included, and we get to see the diffraction pattern. So it's really simply just ray trace through the aperture and just make sure you have enough samples across the point of interest, the aperture. Looking at a slightly different example, but with the same message, here is a very simplistic, representative version of a Cassegrain telescope with some housing. And the interesting thing here is with these 3 struts that are in place for the secondary mirror, diffraction around those struts can also cause image degradation on the detector. So let's just show how we can do that as well. So without the struts, if we just do a ray trace with the secondary mirror magically floating in space, the PSF is very simply rotationally symmetric. So that's as you expect there. And then the question is, if we include the diffraction effects around the struts, what sort of diffraction effects do we see? So again, what we have here is on the left is a ray trace picture, just to show we're actually doing a ray trace. But we have 3 rows of data here, and it's very similar in concept to the triangular aperture. The key point is making sure we have enough samples across the grid to adequately sample, in this case, the object that's blocking the beam. So if we have a grid of 31 by 31 rays, it's nowhere near sufficient because the diffraction pattern is not quite as you expect. It's still showing some sort of diffraction effect, but it's not quite converged to the right answer yet. And then as we increase the sampling to 101 by 101 and 201 by 201, you can see how the diffraction effect starts to form and becomes very clear. So again, the key point is sampling with the number of Gaussian beamlets so that the width and the shape of the obscuration in this case is handled correctly. And then you can see here not only the shape of the diffraction pattern, but also the values we're talking about. What we have here is a log scale and 10 to the minus 6. This is the same data on 10 to the minus 5. So actually we have the same data here, 10 to the minus 8, 10 to the minus 6, 10 to the minus 5. So it's the same data, just on two different scales. So using this data here and going back to the previous slide, comparing to 10 to the minus 4, we can understand essentially the contribution in terms of the image degradation, etc. And that's a more representative case of actually doing something in terms of virtual prototyping in Fred rather than just a triangular wrapper in front of a lens. So just a couple more very simple examples, and then I'll get to a live demonstration. Just to clarify what we're talking about here, diffraction. This is an image from this reference below. Basically, it should be known to most of us here that the three diffraction regions, Fraunhofer region in the far field, which is what we've just looked at because we're focusing down through a lens. And we have Fresnel regions in the intermediate space between what's called the near field, close to the aperture, and the far field. And often the Fresnel region is more complex to calculate correctly because you have a lot more higher spatial frequencies in the diffraction pattern as the beam is in the intermediate state between the aperture and the far field, the Fraunhofer region. So it starts to mutate, and the position in the Fresnel region determines, among other things, determines the fringe pattern that you would see. So just to prove that Fred can also do that, I just got a couple of very simple examples. Again, the key point is making sure you have enough coherent beamlets so that when you sum them together, they produce the right pattern. So a very simple case here of a circular aperture of 1 millimeter semi-aperture and at a wavelength of 0.5. What we can see here is at Z equals 100 millimeters, the cross-section view of the diffraction pattern, which is obviously rotationally symmetric, the cross-section is displayed and matches the theoretical pattern that we expect. The key thing here is to get this accurately, I needed to use a grid of 601 by 601 beamlets, which is quite high for a coherent ray trace, but certainly achievable without too much computational hassle. And then at Z equals 400, further as we approach the far field, the pattern starts to calm down, let's say, and I can get to see the expected diffraction pattern. And also note that I only needed 101 by 101 grid if I wanted to save a little bit of calculation time, because the pattern is a little bit simpler. But certainly Fresnel diffraction is also an option that's possible. Here's just another example of Fresnel diffraction in Fred. At the image plane, well, essentially around the image plane on the soft side and the hard side against towards the lens or further away from the image plane, Fred can easily calculate as a sequence just a simple series of the Fresnel diffraction patterns. And here I've just got a simple example of how what we do if we jump 1 millimeter in each direction, in this direction, I guess 0.5 millimeter in this direction. And you can see how the diffraction pattern evolves in this case. So again, analyses like this, no trouble with Fred as long as you have enough rays so that you have a nice converged solution. Okay, let me flip over to Fred and I'll do a couple of live demos so you can see Fred in action. So we're going to start with the simplest one, and essentially just doing some aperture diffraction. And I've opened the Fred model and you can't see anything because what happens is if I fit the source to view, all right, there's my source. And actually the only other thing in this model is in the analysis surfaces folder on the left side, just an analysis surface to do the calculation at 2.5 kilometers away from the source. So in the far field. And really, that's all I need to do a diffraction simulation of a circular aperture. It's really quite straightforward. The fact that I've defined a coherent plane wave, this is a plane wave source, of this aperture size is equivalent to an infinite plane wave passing through a circular aperture. So I've already, just from the source choice, will be including diffraction effects. And just to prove that, all I'd need to do is create the source, calculate the irradiance, and here at 2.5 kilometers in the far field, put it on a log scale, and there's the expected Airy function. So really, it's completely built into the system. If I open the source again, now switch the aperture shape to rectangle, I can now do the same simulation, but for a square aperture of the same size. Okay, let's put it on a log scale, and we should see a different diffraction pattern. And here we are. So really, it's built into the system. The user doesn't have to do anything special, just has to make sure that they choose the right type of source, in other words, a coherent source type. And in Fred, the groups of sources are split into coherent and incoherent. So that's pretty much the only choice that the user has to make, except for the number of samples, in other words, beamlets or rays across the grid. Make sure that that is sufficient just by doing a couple of convergence tests. Let's do something that's just slightly more interesting now. I've got 3 short examples. This is the second one. And this is calculating a classic effect called the spot of Arago. So what we have here again, very simply, we have a plane wave source, square aperture, and right in front of it, we have an obscuration, essentially a blocking surface just in front. So all this red area here is actually the source rays ready to be traced. And then at z equals 400, I think, we just have an analysis surface here. So with the spot of Arago, it's a diffraction effect that actually creates a peak on the center behind the obscuration, which without diffraction effects wouldn't be there. So again, we just do a ray trace, plot the irradiance at the position at z equals 400. This takes, I'm using a lot of rays and quite a lot of samples to get a decent enough resolution. It takes about 10 seconds in this case, maybe a touch longer. So please bear with me. When I said 10 seconds, I meant 25 or 30 seconds, but there we go. So interestingly, at the z equals 400, we see the different, obviously we can see the effect of the obscuration, the circular blocking surface. But you can see here right at the center and more easily in the cross section, we see this this spot of Arago, as it's called, or Poisson spot, as another term for it, right at the center there, which if this was a geometrical incoherent ray trace, obviously no rays would actually enter this region, and therefore you wouldn't be able to see this. And I do want to clarify, it's not like the rays are bending around. So I use a lot of rays here, but let's drop it down to something we can manage. Let's just do 51 by 51 and actually draw the rays. So it might be a little bit difficult to see, but the rays themselves are not propagating in this area. You see there's kind of a hole here. What's happening is the Gaussian beamlets that are passing around the obscuration, when they get to this analysis surface, we are coherently summing them up, and that coherent sum is creating that interference or diffraction effect, showing us the spot of Arago. So it's not like the rays themselves are bending around, it's just the field as it's propagating in the Gaussian beam decomposition method is also diffracting because they're Gaussian beams, and that diffraction effect is inherently included, and therefore we get to see power where rays don't actually exist in this effect. Okay, I've got time for one final example. This is a slightly different example, but it's quite interesting. So here we have a very simple interferometer, beam splitter, test mirror, reference mirror. Beams come back, combine onto the detector and gives us an interference pattern. So let's check that. Yep. So there's fringes that we expect in just the fact that we know this is an interferometer. Now, the interesting thing is, let's say we want to model on this output surface a single dust particle and include the diffraction effects from that. The challenge becomes a single dust particle of 100 microns or 200 microns, whatever the size is. Obviously, we cannot sample that spatially. They would require us to have incredibly tiny Gaussian beams, incredibly large number of Gaussian beamlets, which just wouldn't be practical. So how would we model this? Well, there's a principle called Babinet's principle, which essentially tells us that the diffraction from an aperture is equivalent to diffraction from an obscuration of the same size. So what we can do as a way to get around this is actually turn that dust particle into a source, a diverging source. So here we have the original laser source, and here I've got a second source located on this surface at a divergence angle. And based on the size of the particle, I calibrated the power based on the area of the particle relative to the area of the beam. And what we can do is actually trace both sources at once. So the blue rays you see here in this triangle is actually from the source. And what we can do is look at the interference pattern as they both combine on the detector. So first, let's look at it using the same settings we had before. Can't really tell anything yet because the particle is so small, it's actually quite a weak power value. If I put it on the log scale, I can certainly see in the center here, there's some sort of diffraction effect or that we don't really have a resolution for just yet. So let's zoom in on this area here and just have a look at the type of power levels and diffraction pattern that we see. And I've got a smaller detector and a much smaller XY size. And what we can see here is this is essentially the interference pattern between that second beam interfering with the plane wave. So the divergent beam from the dust representing diffraction from the dust particle interfering with the plane wave. And this is right in the center of that interference pattern. And we're talking quite low power values here, maybe 1/100th, 2 orders of magnitude below what we saw, but suddenly it might be an effect that you need to consider and therefore model in FRED. So just to clarify, instead of actually modeling a physical dust particle, we use Babinet's principle to represent it by actually a diverging source of the right power value, and then use that to interfere the two beams and see the resulting fringes and interference pattern there. So I've kind of crossed the line, blurred the line between diffraction and interference in this example, but it's a nice example there. Okay, so let me just wrap up. I know this is just a brief taste of FRED, but hopefully it gives you a couple of interesting thoughts about how you can do these types of simulations in FRED. So quickly, some general comments on FRED for physical optics modeling. We use Gaussian beam decomposition, which is a flexible technique that is non-sequential. And it's simply the choice of source that determines if the beam is coherent. So I use a coherent source, and then it's the sampling, the number of beamlets in the source that are essential for ensuring accuracy in the diffraction pattern. And the key thing is that diffraction and interference effects are automatically included. There's no special switch on or technique that the user has to use. So a lot of this content is sampled from what we have as a 3-day physical optics modeling course, where we, for 3 days, talk about these sorts of topics and more, and how to simulate them in FRED. And we have a physical optics course coming up. So if you're interested in what you see here and need some more time to expand on it with more complex examples, more explanation across 3 days, the course that we're running is on November 29 to December 1st. And I'll be the teacher. It's an online course. and let's say 3 days of advanced Fred modeling for this sort of topic. The registration deadline is the end of next week. So if you're interested in this, you like what you see here as a taste, please consider this. There's more details about the synopsis and the content on the website at this link here. And please let us know if that might be something that interests you. So I hope today's been very interesting for you. There's only so much we can get done in half an hour, but I hope that it was valuable. And just please let me know if you have any questions. I'm happy to be online for the next few minutes and answer whatever questions come in. So again, thank you for your time. Okay, one question that's come in. It's a question about the GPU ray tracing on Fred MVC. Two things. It's a very fast calculation. Obviously, it depends on the GPU, but honestly, for typical real models with hundreds or thousands of surfaces and needing to trace hundreds of millions of rays, it's easily 100 times faster and maybe 1,000 times faster than a CPU ray trace. The only caveat to that is the GPU ray tracing of Fred MVC does not do the coherent calculations. Quite simply because the coherent calculations, as you saw in these demonstrations, really don't take that much time and almost never require hundreds of millions of rays. So it's never been a priority for the GPU ray tracing, but potentially in the future it will be added. The only caveat to that caveat is what we have done in Fred MVC is put the irradiance calculations on the GPU. So you remember when we did the spot of Arago and we had to sit waiting for 25, 30 seconds? That can be done on the GPU now. Just a little toggle button saying calculate irradiance on the GPU. And that has a factor like maybe 10 to 20 times faster processing time. So that is the one benefit of using Fred MVC for physical optics, is the irradiance calculations, which often can take longer than the coherent ray trace. Oh, just to clarify the conversation before we move on to the next question. What I showed you today with that spot of Arago calculation, that 25-second calculation, that was just on the CPU. So in theory, if I didn't want to wait 25 seconds, I could have switched on to do it on the GPU and it would have taken 2 or 3 seconds. Another question, can you have diffraction effects also by using the Gaussian laser type source? Yes. Really, any of the coherent source types. I just used a plane wave in these examples with the assumption that it's a top hat or a plane, infinite plane wave coming through the aperture. But if this was a fundamental mode of a Gaussian or something even more complex, yes, the diffraction effects are automatically included. So I kept it simpler in these examples, but there's no reason why I needed to do that. So Gaussian fundamental mode or higher order modes set up the source type. As long as it's coherent and you have enough samples, you will see the diffraction effects. Okay, a great question has just come in. Is there a way to model diffraction on a 2D grid as what would happen when light is diffraction on a pixel structure of an imaging sensor? To model diffraction on a 2D grid, basically a 2D grating, and clarify if I'm misunderstanding the question, but grating structures are not explicitly modeled in Fred. Like all other ray tracing software, you enter the data for the period of the grating and the diffraction efficiency values as a function of wavelength and so on. But then Fred just solves the grating equation. So we're not explicitly modeling the grating, the physical step structure of the grating or the blaze structure. So it's not a physical optics simulation. You can model this in Fred by essentially putting two gratings, two 1D gratings on top of each other very close. And the overall effect, and if it's set up correctly, the overall effect is that you can model a 2D diffraction pattern. But just to clarify, we are not modeling it coherently, and we're not explicitly modeling the actual grating structure. That just is beyond both ray tracing and also Fred's Gaussian beam decomposition. To do that correctly, you need to use something, a grating design software that uses something like RCWA, which is rigorous coupled wave analysis, or FTTD, or something that is purely electromagnetic rigorous solving. So you can do this in Fred, but you're doing it by overlaying two 1D gratings in such a way that we get the expected diffraction pattern. But the complex thing is that even to do this, you need to know the diffraction efficiency of the grating, which needs to be calculated elsewhere or measured elsewhere. And I can send you a very simple example of that. I've got a couple of slides to the person who asked the question. I got a couple of slides that I can send to you, just to outline what I mentioned there. Okay, I'll just wait another 30 seconds or so, see if there's anyone with a question coming. If not, let me just start wrapping up and say thank you for your time. Please feel free to email us if you have any questions or comments, and just keep in touch. And look forward to being on a webinar or seeing you in the course again soon. Thank you.